Hello, and welcome to my video presentation of small modular reactors. My name is Brad Timmis, and today we're going to go over the pros and cons of using a small modular reactor and comparing them against light water reactors. Here on the right you can see the Westinghouse 225 megawatt electric SMR, and as you can see, the pressurizer is built right into the reactor core. The reactor core is at the bottom, and I believe this vessel uses natural convection to circulate the water. Quick overview of what we're going to talk about today. I'm going to go over what a small modular reactor is, available small modular reactors on the market right now, light water reactors, the pros of small modular, the cons of small modular, a conclusion, and then my reference page. So small modular reactors. They are reactors that are able to be factory built and then assembled on site. Small modular reactors generally means 300 megawatts or less of electrical energy output. Submarines, aircraft carriers, icebreakers, and universities already use SMRs. Available SMRs on the market. We have the Holtec SMR 160. It's got a small footprint of 4.5 acres and produces 160 megawatts of electricity. The NuScale is a smaller reactor and it produces 45 megawatts of electricity and uses no pumps, only natural convection cooling of the core. And the Westinghouse SMR, which we saw on the front page, was a small modular reactor that can output 225 megawatts of electricity. So start off first with the SMR 160. It's developed by Holtec International in the United States. It uses a low enriched uranium fuel to produce 160 megawatts of electricity. It requires a minimum of 4.5 acres. It uses cooling water from a natural source. It is a pressurized water design, which means that the cooling water and the water that is converted into steam that goes through the turbines are separated. And it uses gravity instead of pumps to ensure a fail-safe operation at all times. And here is the Holtec SMR 160. On the left you can see the reactor design, and on the right you can see the configurations for the pressurized water reactor. And the bottom one, boxed out in the red dots, is the vessel that they use. You can see where the reactor on the right and the power lines on the left are separated, involving two main water lines. Next, we have the NuScale, which also uses natural convection to cool the reactor, and it also has helical coil steam generators. The reactor itself is 65 feet tall and 9 feet in diameter. There's no motors or pumps in the system. It produces 50 megawatts of electricity, and it uses standard light water reactor fuel and a 17 by 17 configuration with a 2-year refueling cycle. Here you can see the NuScale reactor on the left with the power module, and you can also see the proposed NuScale plant layout on the right. So with the Westinghouse SMR, it has safety features that include shutting down the plant automatically, and it can keep cool for up to 7 days with no outside power or human activity needed. It produces 225 megawatts on 15 acres of land, has a design life of 60 years with refueling every 2 years, and the reactor itself is 81 feet tall and 11.5 feet in diameter. In this photo here, you can see the Westinghouse SMR on the left, and on the right you can see a land use comparison with other renewable energies, such as solar and wind. So moving on to light water reactors, we have our two main types of reactors, the boiling water reactor and the pressurized water reactor. I'm sorry for the quality of the photos on there, it's a little blurry. But for the boiling water reactor, you have a water line that goes from the reactor, turns into steam, goes through the turbine, is condensed, and returns. Whereas in the pressurized water reactor, The water that's in the reactor core and interacts with that is separated from the water that goes through the turbine and generator. So a boiling water reactor, like I said, the water in the core boils off and then that steam is converted to electricity. There are 34 boiling water reactors in use in the United States today. And since boiling is the only method of heat removal, a large torus around the base of the reactor cores are required in case you have to flood the system and suppress any steam. A pressurized water reactor, the water lines are actually separated and the water in the core heats up water in a different unit in order to flash that to steam and drive your turbines. There are 65 pressurized water reactors in use today, and that wraps up the light water reactor. For the pros of small modular reactors, they allow for flexible power generation in small blocks. Once they are installed, they will provide a steady and reliable amount of electricity onto the grid. The smaller size makes manufacturing, transportation, and assembly easier and more economic. SMRs are very attractive for remote areas requiring electricity and process heat, where the excess heat left over around the reactor and the water lines and the steam lines, you can use that sometimes and run other processes. And in Alaska, for example, you can use that heat to heat buildings or anything like that. The long refueling cycles of small modular reactors requires less fuel handling, which is a benefit for everyone involved. And the small size reduces the radioactive risk to within the plant area, since there's not enough radiation in the core for there to present a large risk. Some cons of small modular reactors: the risk of nuclear proliferation is high, requiring a full-time security presence on site. That should be pretty self-explanatory when you're dealing with nuclear reactors, and especially small ones that are possibly in remote areas. You don't want the spent fuel to have any fissile materials that could be reprocessed and used for nefarious purposes. Spent fuel storage solutions are generally temporary, and a long-term solution requires a large space, which is a little bit against what the small modular reactor is trying to do. It wants to reduce the space involved in a nuclear power plant, and requiring a long-term spent fuel storage pool on site would increase the area needed. Another con of the small modular reactors: there's a higher operating cost per megawatt produced compared to large traditional nuclear plants. And bringing more reactors online on one site would require additional control personnel on the same site to make sure that all the reactors are being monitored 24/7. So in conclusion, small modular reactors are cheaper, faster, and smaller to manufacture, transport, and assemble, but are more costly per megawatt electric to operate compared to traditional nuclear reactors. The small size allows for less fuel in the core and longer refueling cycles. There are still unsolved problems facing security, personnel needed, and finding a market where a small nuclear source is viable. And proliferation and spent fuel storage are omnipresent concerns with nuclear power, and SMRs do not solve those problems, but that is to be taken into consideration when dealing with nuclear power anytime. So here are my references. Thank you for tuning in and watching the video, and another thanks to Dr. Sutton for giving me this assignment and project. It's been a great semester. I'm Brad Timmis, and thank you very much.